Imagine it's the middle of winter. The snow is piled high against the walls. The wind is coming in through every crack in the timber. You are sitting in a room with no windows, no insulation, no central heating, no thermostat, and no particular expectation that you will be warm. There is, however, a small fire in the middle of the floor. The smoke is going somewhere. You are not entirely sure where. There is a brazier in the corner that the family has been huddling around since before dawn. There is a woolen blanket on your shoulders that has been in the family for 3 generations. Your grandmother is brewing something that smells faintly of vinegar. You are going to be cold today. You are going to be cold tomorrow. You are frankly going to be cold for most of the next 4 months. Welcome to Climate Control Ancient Edition. But here's the thing. The ancient world did not sit still in the cold. People did not simply endure. They experimented. They invented. They built, with great ingenuity and considerable expense, systems for heating and cooling their homes that were, in their own way, remarkably sophisticated. Some of these systems worked better than others. Some of them were astonishingly good. And the story of how humans learned to manipulate the temperature of their living spaces, without electricity, without refrigeration, without anything resembling modern HVAC, is one of the great unsung sagas of engineering history. For most of human prehistory, the answer to the question of how ancient humans heated their homes was extremely simple. Fire. You had a fire. The fire was in the middle of the room. The smoke went up to the ceiling and then, ideally, out a hole in the roof. The technology was, depending on how you look at it, either brilliantly minimal or profoundly inadequate. The reality, for most early humans, was that they lived in climates and structures where the fire was sufficient. In much of Africa, the Middle East, and the Mediterranean, winters were mild enough that a fire for cooking was also a fire for warmth. People sat near it. They slept near it. They organized their lives around it. The fire was the center of the home, both literally and socially. The earliest houses in places like Çatalhöyük in modern Turkey, around 7,500 BC, were built of mud brick and had no chimneys. The hearth was in the middle of the room, and the smoke rose to the ceiling and slowly seeped out through the roof and the walls. The walls and ceilings of these houses were blackened with soot, sometimes inches thick, because the smoke never fully cleared. The inhabitants must have had remarkably strong lungs, or they must have spent a lot of time outside, or both. There is some evidence that they kept small livestock indoors, particularly in winter, which would have generated some additional warmth, although it would also have generated a great deal of additional smell. The first major improvement on the open hearth was the hypocaust, which was a Roman invention and one of the most important heating technologies in the ancient world. The hypocaust was a system of raised floors supported by small pillars of stacked tiles. Underneath the floor, a furnace would burn wood or charcoal, and the hot air would circulate through the space beneath the floor, heating it from below. The hot air would then rise through flues built into the walls, providing additional heat, and would finally exit through vents in the roof. The effect was essentially radiant floor heating, 2,000 years before the modern version. The hypocaust was developed in the late Roman Republic, around the 1st century BC, and it was used extensively in Roman baths, in wealthy private homes, and in some public buildings. The system worked remarkably well. The Roman architect Vitruvius, writing in the 1st century BC, described the hypocaust in detail in his treatise De Architectura, and his description is detailed enough that modern engineers have been able to reconstruct the systems with considerable accuracy. The bath at Bath in England, which was built around the natural hot springs, used a hypocaust-like system to maintain its temperature, and the remains of the system are still visible today. The Roman soldiers stationed in the cold northern provinces of Britain were presumably very grateful for the technology. The hypocaust was not cheap. The system required substantial construction. The floor had to be raised. The pillars had to be built. The furnace had to be maintained. The fuel had to be supplied. Only wealthy Romans could afford the system, and even then, only in certain rooms. The wealthier the household, the more rooms were heated and the more elaborate the system became. Some wealthy Roman homes had multiple furnaces, with different rooms heated to different temperatures, which is essentially climate zoning, applied to a Roman villa. The Romans also developed the practice of double glazing, although for a different reason than we typically associate with it. Roman window glass, made by casting rather than blowing, was thick and cloudy. It let in light but distorted the view. For wealthy Romans, the distortion was a feature, not a bug. It prevented outsiders from seeing in. For the windows of bathhouses and other heated rooms, however, the glass served a practical purpose. It trapped heat. The baths at Pompeii, which were heated by hypocausts, had glass windows, and the glass helped retain the heat. This is the first recorded use of glass for thermal insulation, although the Romans would not have called it that. The Chinese, independently of the Romans, developed their own heating systems. The kang, which was a raised platform made of brick or stone with flues running through it, was heated by a fire at one end, and the smoke and hot gases would travel through the flues before exiting through a chimney at the other end. The platform itself would become warm, and the family would sit or sleep on it. The kang was particularly common in northern China, where winters were long and cold, and it was an extraordinarily efficient use of fuel. The heat was retained in the brick for hours after the fire went out, and the family could sleep on a warm surface even in the middle of a freezing night. The kang was not just a heating device, it was a piece of furniture. It was a bed, a couch, a meeting place, a place to do business. In a northern Chinese home, the kang was the center of domestic life. The family slept on it, they ate on it, they received guests on it, they worked on it. The kang was warmer than any other part of the house, so that is where everyone gathered. The most honored seat was the warmest seat, which was the seat closest to the firebox. The kang was a piece of social architecture as much as it was a piece of physical architecture. The Chinese also developed the concept of the heated brick bed, which was essentially a portable kang. A small metal stove or brazier would be placed in a hollowed-out space in the brick bed, and the bed would warm up. Travelers in winter would sometimes carry small heated brick beds with them, or stop at inns that provided them. The heated brick bed was, in some sense, the original electric blanket, except powered by fire. In Japan, where winters could also be cold, particularly in the northern regions, the traditional heating system was the hibachi, a small portable brazier that burned charcoal. The hibachi was used to heat individual rooms or even individual people who would huddle around it or hold it under a blanket. The Japanese also used the kotatsu, a low table with a heat source underneath and a heavy blanket draped over it. The family would sit around the kotatsu with their legs under the table, and the blanket would trap the heat. The kotatsu was extraordinarily efficient because the heat was concentrated exactly where the family was sitting. The rest of the house could be cold, but the family was warm. The kotatsu was, like the kang, more than a heating device. It was a piece of social architecture. In a Japanese household, the family gathered around the kotatsu in winter, and the conversations, decisions, meals, and quiet evenings all took place there. The kotatsu was the warm heart of the house. The rest of the house, even in the coldest weather, was often unheated. People wore extra clothing. They wore tabi socks. They wore haori jackets. They endured the cold in the unheated rooms and welcomed the warmth of the kotatsu when they could. The Koreans developed a similar system called the ondol, which is the origin of the word ondol in Korean and which is the direct ancestor of the modern Korean underfloor heating system. The ondol was a network of flues running under the floor of the house, heated by a fire at one end. The smoke would travel through the flues and exit through a chimney. The floor itself would become warm, and the family would sit, eat, and sleep on it. The ondol was extraordinarily efficient and extraordinarily well suited to the Korean climate. It is still used in modified form in many Korean homes today, although the modern version uses hot water or electricity rather than smoke. The Persian Empire, which was centered in a region with hot summers and cold winters, developed an extensive set of cooling technologies, partly because the wealthy Persian kings and nobles demanded comfort in all seasons. The Persian Karnat system, which was originally developed for irrigation, also had the side effect of cooling the air. A Karnat is an underground channel that carries water from an aquifer to a surface location. The water in the Karnat is cool because it has been underground and out of the sun. As the water emerges at the surface, it cools the surrounding air, and the cool air can be channeled into buildings through vents and shafts. This is essentially geothermal cooling applied to a desert environment, and it worked remarkably well. The Persians also built the badgir, which was a wind catcher, a tall tower with openings designed to capture the prevailing breeze and channel it down into the building below. The badgir was used extensively in the city of Yazd in central Iran, where summer temperatures routinely exceed 40 degrees Celsius. The wind caught by the badgir would be channeled down into the rooms below, and in some cases, the air would be passed over water or through qanats to cool it further. The badgir was, in some sense, the original air conditioner, except it was powered by the wind rather than by electricity. The Persians also used the yakhchal, which was a kind of ancient ice house. The yakhchal was a domed structure with thick walls, often made of a special mortar that was resistant to heat transfer. The interior was below ground level, and water would be brought in during the cold winter nights and frozen. The ice would be stored in the yakhchal through the summer, and it could be retrieved for use in drinks, in food preparation, and in the cooling of food. The yakhchal was, in essence, a refrigerator without electricity, and it could keep ice for months, even in the desert heat. The yakhchal is sometimes credited with inspiring the design of the modern refrigerator, and there is a real sense in which the technology is the same. You build an insulated space, you put something cold in it, you keep the heat out, you retrieve the cold thing later. The yakhchal worked on the same principle as a modern refrigerator, and it was in use in Persia for more than 2,000 years. The technology did not require any particularly sophisticated scientific understanding. It required careful construction, the use of appropriate materials, and a reliable source of cold water in the winter. The Persians had all three. The ancient Egyptians, who lived in a hot climate, also developed techniques for cooling their homes. The Egyptians used the mashrabia, which was a kind of projecting oriel window with a lattice of turned wood. The lattice allowed air to circulate but blocked direct sunlight, and the projection of the window kept the interior cool. The mashrabia was also used in other parts of the Islamic world, particularly in the Middle East, and it remained in use in some places into the 20th century. The mashrabia was, in some sense, the original sunscreen. The Egyptians also used water features for cooling. Wealthy Egyptian homes had pools, fountains, and water channels in their gardens, and the evaporation of the water cooled the surrounding air. The Egyptians understood, instinctively if not scientifically, that water cools the air around it, and they used this property to make their homes and gardens more comfortable in the heat. The pools in Egyptian gardens were not just decorative, they were functional. They were the air conditioning of the ancient world. The Romans, in addition to their hypocausts, also developed cooling techniques. Wealthy Romans had running water in their homes, supplied by aqueducts, and the water could be circulated through pipes in the walls or under the floors to cool the rooms. The Romans also used the peristyle, which was an open courtyard surrounded by columns, often with a pool or fountain in the center. The peristyle allowed air to circulate through the house, and the water in the pool cooled the air. The peristyle was, in some sense, the ancient version of a central air conditioning system, except it used moving air and water rather than refrigeration. The Romans also used a substance called garum, which was a fermented fish sauce, not as a coolant, but as a way to mask the smell of poor water. The Romans were, in general, less concerned with cooling than with heating, because most of the Roman Empire was in temperate climates where heating was the bigger problem. The Romans did develop some clever tricks for cooling, however. They would hang wet sheets in doorways and windows. The evaporation of the water would cool the air as it entered the house. They would also place containers of snow or ice brought down from the mountains in front of fans. The slaves would fan the air across the ice, producing a cooling breeze. This is the original air conditioner, and it was used to cool the rooms of wealthy Romans during the summer. The Greeks, particularly in the classical period, had less elaborate climate control systems than the Romans or the Chinese, but they did develop some effective techniques. Wealthy Greek homes in cities like Athens had internal courtyards, often with pools or fountains, that helped cool the surrounding rooms. The Greek houses were also often built with thick walls, made of mud brick or stone, that absorbed heat during the day and released it at night, keeping the interior cooler than the outside air. The orientation of the house was also considered. Greek architects were aware that south-facing rooms got more sun in winter and could be cooler in summer if shaded, and they oriented their houses accordingly. The Greeks also used vegetation strategically. They planted trees and vines around their houses, not just for decoration, but for shade. The shade from the trees would keep the walls of the house cooler, and the evaporation from the leaves would cool the surrounding air. The Greek practice of planting plane trees around houses was not just aesthetic, it was a cooling strategy. The Romans took the Greek idea further. Wealthy Roman villas had extensive gardens, often with carefully planned plantings that provided shade and cooling. The villas at Pompeii and Herculaneum had gardens designed not just for beauty, but for climate control. The plants were chosen for their shade-giving properties. The water features were designed for their cooling effects, and the orientation of the house was carefully considered to maximize the prevailing breezes. The Roman villa was, in some sense, a complete climate-controlled environment, designed to be comfortable in both summer and winter. The Romans also used a substance called opus signinum, which was a kind of hydraulic cement made from volcanic ash, lime, and crushed pottery. Opus signinum was used to line pools and water channels, but it was also used as a floor surface. The cement had the property of staying cool to the touch, even in hot weather, because it absorbed heat slowly. A floor of opus signinum would be noticeably cooler than the surrounding air, and walking on it barefoot was pleasant in summer. This is, again, the original cool floor, and it was in widespread use across the Roman Empire. The Minoans on the island of Crete developed an early form of climate control in their palaces, particularly at Knossos, around 1700 BC. The palace at Knossos had a complex system of light wells, air shafts, and columned halls that were designed to allow air to circulate through the building. The light wells admitted sunlight, but were oriented so that direct sunlight would not enter the rooms. The air shafts allowed hot air to rise and escape, drawing cooler air in from below. The result was a building that was noticeably cooler than the surrounding countryside in summer. The Minoans were, in some sense, the first climate engineers. The Romans copied the Minoan idea. The Roman atrium, which was the central hall of a wealthy Roman house, was designed with a compluvium, an opening in the roof, and an impluvium, a pool in the floor beneath the opening. The opening allowed hot air to rise and escape, and the pool helped cool the air that came in. The atrium was, in some sense, an air conditioner, drawing cool air from below and expelling hot air above. The system worked remarkably well, and it is one of the reasons why Roman houses, even in the heat of summer, were often comfortable. The medieval period in Europe saw a regression in climate control technology, partly because the Roman systems had been forgotten, and partly because the political and economic conditions of the period did not support large-scale engineering projects. Medieval European homes were often heated by open fires, with smoke escaping through a hole in the roof or through a simple chimney. The chimney was, in fact, a medieval invention, and it was a major improvement over the open hearth. Before chimneys, the smoke from the fire filled the room, and the inhabitants had to endure it. After chimneys, the smoke was vented outside, and the room could be heated without being smoked. This was a huge improvement, and it is easy to forget in our modern world of central heating what a major advance the chimney was. The medieval Japanese developed the onsen, which was a hot spring bath. The onsen was used both for bathing and for heating. The water from the hot spring would be channeled through the house, and the warm water would heat the rooms. The onsen was, in some sense, the original central heating, except powered by geothermal heat rather than by combustion. The onsen was also used for cooking and for washing, and the entire house could be organized around the hot spring water. The Incas in pre-Columbian South America had a different approach to climate control, partly because they lived in a wide range of climates, from the hot coast to the cold highlands. In the highlands, where temperatures could fall below freezing at night, the Incas built their houses of stone with thick walls that absorbed heat during the day and released it at night. The interior of the houses could be considerably warmer than the outside air, simply because of the thermal mass of the walls. The Incas also used the hearth extensively, and they developed a kind of underfloor heating system similar to the Chinese kang, with hot gases from the fire circulating under the floor before exiting through a chimney. The Mayans in the lowland tropics of Central America had the opposite problem. They needed to cool their homes, not heat them. The Mayan houses were typically made of stone or thatch, with high ceilings and small windows. The high ceilings allowed hot air to rise above the inhabitants, and the small windows kept direct sunlight out. The Mayans also used the technique of sleeping outdoors in the warm months, which is not technically a climate control technology, but is a remarkably effective one. The Romans, for all their heating technology, also relied heavily on clothing and bedding for warmth. Romans wore multiple layers of wool and linen in winter, and they slept under heavy blankets. The Roman army, in particular, was expert at keeping warm in cold climates, and the Roman soldiers' standard equipment included a heavy woolen cloak, leather boots, and a fur-lined hat. The Romans understood that clothing was the first line of defense against the cold, and that the most sophisticated heating system in the world was of limited use if you were not dressed appropriately. The Greeks had a similar approach. The Greek cloak, the himation, was a large rectangular piece of woolen cloth that could be wrapped around the body in multiple ways. In winter, the Greeks would wear multiple layers of himation, and they would pull the cloth up over their heads to keep warm. The Greek concept of warmth was not just about temperature, it was about coverage. The more of you was covered, the warmer you were, regardless of the temperature of the surrounding air. The Chinese, like the Romans and the Greeks, also relied on clothing, but they had a particular fondness for layered silk garments. Silk was warm, lightweight, and comfortable against the skin, and it was the preferred material for the inner layers of winter clothing. The wealthy Chinese in winter would wear silk next to the skin, with wool or fur over it, and they would be warm even in unheated rooms. The Persians, in the cold winters of their highland regions, developed an extensive clothing culture designed for warmth. The Persian cloak, the kaba, was a heavy woolen garment, often lined with fur, that could be wrapped around the body. The Persians also wore multiple layers of linen and wool, and they used the technique of layering in, a way that was both practical and fashionable. Persian clothing in winter was both a heating technology and a status symbol. The finest Persian winter clothing was lined with the softest furs, and the quality of the fur was a clear indication of the wearer's wealth. What stands out looking at all of this from a distance is how creative and resourceful ancient humans were, given the constraints they faced. They did not have electricity. They did not have fossil fuels, except in limited quantities. They did not have the modern understanding of thermodynamics that we now take for granted. But they had observation. They had experimentation. They had generations of accumulated practical knowledge, and they used these resources to build homes that were, in many cases, remarkably comfortable. The Chinese kang, the Roman hippocaust, the Persian yakchal, the Japanese kotatsu, the Korean ondol, the Minoan lightwell, the Greek peristyle. These were not minor achievements. They were major engineering works, designed and built by people who had only their hands, their tools, and their experience to work with. The hypocaust, in particular, was a brilliant piece of engineering, and it remained in use in various forms for almost 2,000 years. The yakchal was, in some sense, a refrigerator, and it worked on principles that we still use today. Modern climate control has, of course, made most of these technologies obsolete. We have central heating, we have central air conditioning, we have refrigerators and freezers, we have insulation, double glazing, and programmable thermostats. We take all of this for granted. We flip a switch and the house is warm. We flip another switch and the house is cool. We do not think about the engineering that makes it possible. We do not think about the history. But the ancient systems are still with us, in form if not in function. The radiator is the descendant of the hypocaust. The kotatsu is still in use in Japan. The kang is still in use in northern China. The yakchal principle is the principle behind the modern refrigerator. The mashrabia is still in use in some parts of the Middle East. The wisdom of the ancients, in this as in so many other things, has not been entirely lost. It has just been upgraded. Almost, just with better thermostats. Subscribe if you like this video.